For mixture separations in fixed bed adsorbers packed with microcrystalline adsorbents such as metal organic frameworks or zeolites, it is often important to model the intra-crystalline diffusion influences properly. This is specifically of importance for kinetic separations where diffusion influences serve to reverse the hierarchy of adsorption strengths dictated by mixture adsorption equilibrium. In several presentations that I have uploaded on my YouTube channel, I have stressed the need for the use of the Maxwell Stefan diffusion formulations. I'll list here a few of the video presentations on this topic, and today I'm going to proceed further in looking at the use of the Maxwell Stefan diffusion equations for modeling mixture separations in fixed bed adsorbers by analyzing experimental data on transient breakthroughs. Let's first refresh our memories on the Maxwell Stefan diffusion formulations. In these formulations, the molar flux of any component 1 or 2 in the feed mixture is related to the gradients of the chemical potentials mu1 and mu2 of the guest molecules. The chemical potential gradients are in turn related to the partial pressures P sub I of the gas components in the gas mixture surrounding the microcrystalline adsorbent. The chemical potential gradients can be related to the gradients of the molar loadings Q sub J by defining a matrix of thermodynamic correction factors which are related to the component molar loadings in the adsorb phase and the partial pressures in the bulk gas phase surrounding the particle. These thermodynamic correction factors gamma ij can be determined from expressions that describe the mixture adsorption equilibrium, typically the ideal adsorbed solution theory. The molar gradients in the the gradients in the component molar loadings are related to the chemical potential gradients by a matrix of thermodynamic correction factors. If this matrix of thermodynamic correction factors is taken to be the identity matrix, in other words, the diagonal elements being unity and the off-diagonal elements being 0, we have essentially reduced the complexity of the problem to the Fickian formulation and the LDF approximation that is commonly used in modeling fixed bed adsorbers. In a previous presentation on separation of mixtures of ethene and ethane using cobalt gallate, I had underscored the large errors that will accrue by adopting the LDF formulation. Today, I'm going to present experimental evidence to support that conclusion I had drawn in my previous presentations. The experimental data that I will be analyzing in the subsequent slides consists of a feed mixture of 2-methyl butane, 2-methyl pentane, and 2,2-dimethyl butane in a fixed bed adsorber packed with MFI zeolite. The products leaving the adsorption device is a raffinate phase that is richer in the di-branched isomer that has a higher octane number. The experimental data that I will be analyzing are from this paper by Joly-Maitre, published in the AICHE journal in 2002. All the simulation data that I will present are from my paper, highlighting the influence of thermodynamic coupling on kinetic separations with microporous crystalline materials, published in ACS Omega in 2019. Let's examine the background to this separation, and let's examine the experimental data. MFI zeolite is a suitable adsorbent for separating alkane isomers. MFI stands for mobile 5. It has a set of intersecting channels of 5.5 angstrom. These are the straight channels, and in this direction we have the zigzag channels. These channels intersect at these locations, and there are 4 intersection sites per unit cell. The branched isomers of alkanes, say 2-methyl butane, 2-methyl pentane, and 2,2-dimethyl butane, all the branched isomers prefer to locate at the intersection sites where it has more leg room. This is shown by the computational snapshots here. There are 4 intersection sites per unit cell, and the saturation capacities of the unary isotherms for these 3 isomers are all 4 molecules per unit cell. For 2-methyl butane, the Langmuir constant is 4.12 times 10 to the minus 5 Pascal minus 1. The corresponding Langmuir constant for 2,2-dimethyl butane is higher. It's 7.12 times 10 minus 5. And the Langmuir constant for 2-methyl pentane is even higher than that of 2-methyl butane because of improved van der Waals interactions with the channel walls, and the Langmuir constant is 1.27 times 10 minus 4 Pascal minus 1. However, the diffusional time constants are shown here. These were determined experimentally, and these diffusional time constants are the highest for 2-methyl butane. This lowered slightly for 2-methyl pentane, and the lowest diffusional time constant is for 2,2-dimethyl butane. Therefore, within the intersecting channels of MFI zeolite, 2-methyl pentane has the highest adsorption strengths, but the di-branched 2,2-dimethyl butane has the lowest diffusivity. Let's examine how adsorption strengths and guest mobility play out against each other. And I demonstrate this by examining a set of 6 experiments reported by Joly-Maitre in the AICHE journal paper published in 2002. The analysis I will be presenting is based on my own paper published in ACS Omega in 2019. In these 6 figures, A, B, C, D, E, F, I plot the experimental data of Joly-Metre as published in the AICHE journal in 2002. The experimental data are shown by the symbols. These 2 experiments here are for binary mixtures of 2-methyl pentane and 2,2-dimethyl butane. The experiments show that the component to elute first is 2,2-dimethyl butane that has the lower adsorption strength and also the lower intra-crystalline diffusivity as compared to 2-methyl pentane that has a higher adsorption strength and also a higher diffusion coefficient. The continuous solid lines are the breakthrough simulations ignoring diffusional influences, and we note that the match is poor because diffusional influences are strong. Diffusional influences make 2,2-dimethyl butane elute the adsorber earlier than anticipated by a model that ignores intracrystalline diffusional influences. Indeed, diffusional influences are helpful in the separations because there is a wider gap between the breakthrough times from experiments than those anticipated by a model that ignores diffusional influences. Put another way, adsorption and diffusion act synergistically in runs 17 and 18. The partial pressures indicated here are the partial pressures of the feed mixture at the inlet to the fixed bed adsorber packed with MFI pellets. The experiments shown here, these 4 set experiments run 19, 20, 21 and 22 for ternary mixtures of 2-methyl butane, 2-methyl pentane and 2,2-dimethyl butane. In all 4 experiments, the component to elute first is 2,2-dimethyl butane that has the lowest mobility within the intersecting channels of MFI zeolite. The component to elute last in all 4 experiments is 2-methyl pentane that has the highest adsorption strengths of the 3 components. What is interesting to note is that the simulations in which diffusional influences are considered to be of negligible importance, the component to elute first is 2-methyl butane, but this is not in agreement with the experiments because in the experiments 2,2-dimethyl butane elutes first. This reversal in the order of breakthroughs of 2-methyl butane and 2,2-dimethyl butane is purely ascribable to the significant differences in intracrystalline diffusion due to the significantly lower mobility of 2,2-dimethyl butane within MFI zeolite, 2,2-DMB elutes first. So diffusion overrides the hierarchy of adsorption. And this is also helpful in the separations because we want to recover 2,2-dimethyl-butane for incorporation into the gasoline pool, and due to diffusional influences, the component to elute first and recovered in the raffinate phase is 2,2-dimethylbutane. So diffusional influences help separations. Let us demonstrate that quantitatively in the next slide. To model the breakthrough experiments published by Joly-Maitre, we need to take proper account of both adsorption and diffusion. And for modeling of diffusion inside the micropores, there is a need to incorporate the Maxwell Stefan diffusional formulation, in which due account is taken of thermodynamic coupling effects. And I explained this in my 2019 paper published in ACS Omega. Watch also my YouTube presentation, Diffusion and Micropores. And there are other presentations on diffusional effects in zeolites and morphs that can be viewed on my YouTube channel. The set of 6 experiments can be reproduced nearly quantitatively by a model in which due account is taken of the interplay between adsorption and diffusion using the Maxwell Stefan diffusional formulation, and the predictions of the breakthroughs are shown here by the continuous black lines. For all 6 experiments, there is one-to-one correspondence between experiments and simulations. So I conclude by saying that MFI zeolite is suitable for use in separation of alkane isomers. The separations are synergistic in nature because the diffusional influences serve to enhance the separations that is dictated by mixture adsorption equilibrium. And in my reckoning, MFI zeolite is the most suitable adsorbent for alkane isomer separations. Let us go one step further and compare the simulations in which thermodynamic coupling effects are included with the corresponding simulations in which thermodynamic coupling is ignored, as is done in the LDF approximations that are commonly used in fixed bed adsorber modeling. The continuous black lines are the simulations using the Maxwell Stefan formulations, including thermodynamic coupling. The dashed lines are the simulations using a simplified model, say the LDF approximation, based on the Fick's law, in which thermodynamic coupling influences are considered to be negligible. In all 6 cases, we note that ignoring thermodynamic coupling leads to a very poor match with the experimental data. This strengthens the argument that ignore thermodynamic coupling effects at your own peril. That's the takeaway message from this presentation.